In 1814, a French mathematician named Pierre-Simon Laplace wrote a passage that still haunts physics 2 centuries later. He imagined an intelligence, a hypothetical being that knew every force acting in nature and the precise position of every particle in existence at a single instant. This intelligence, Laplace argued, could, in principle, infer the entire past and predict the entire future from that one snapshot of knowledge. Nothing would be uncertain, nothing would be random. The complete history and destiny of everything would be calculable. This became known as Laplace's Demon, and for a long time, physics seemed to agree with the basic picture. The laws of motion were deterministic. Given initial conditions and the equations of physics, the future followed with mathematical certainty. Randomness was not a feature of the fundamental laws, but an expression of our ignorance, a placeholder for information we lacked about causes we could not see. Quantum mechanics arrived in the early 20th century. The early 20th century brought a new physics that seemed to overthrow determinism at its foundation. Standard quantum theory outputs probabilities for measurement outcomes rather than single outcome certainty. When you measure where a particle will be found, the theory gives you odds, not guarantees. The apparent randomness is not merely practical ignorance, but seems built into the formalism itself. Most physicists accepted this probabilistic picture. Randomness, they concluded, is fundamental. Causes do not fully determine effects at the quantum level. The universe contains irreducible chance. Einstein famously had doubts about this picture, objecting to quantum indeterminism and questioning whether the theory was complete. His skepticism was largely set aside, as experiments confirmed quantum predictions with extraordinary precision. What most people do not realize is that the question is not settled. There exists a logical loophole in the arguments against determinism, a gap in the reasoning that has never been closed by experiment. It is controversial, widely dismissed, and possibly correct. It suggests that what we call quantum randomness might not be randomness at all, but the appearance of randomness arising from causes we cannot access. This is superdeterminism. And by the end of this video, you will understand what it claims, why mainstream physics is skeptical, and why a minority of serious physicists believe it deserves reconsideration. We will explore the Bell tests that seem to prove randomness is fundamental, the cosmic scale experiments that push the question back billions of years, and the philosophical stakes of accepting or denying that true randomness exists. If you find value in explorations like this, in understanding the deep questions that remain open even after a century of quantum physics, consider subscribing to the channel. It helps these deep dives reach more curious minds. Now, let us begin. Let me start with what quantum mechanics actually says about measurement outcomes, because the precise claim matters. Standard quantum theory uses the Born rule to calculate probabilities for measurement results. If you have a particle whose position is described by a wave function, the theory tells you the probability of finding the particle at any given location. It does not tell you exactly where the particle will be found in any single measurement. This probabilistic character is not like the probabilities in classical physics. When you flip a coin, the outcome is determined by physical factors you could, in principle, measure: the force of the flip, the air resistance, the initial orientation. The probability is a shorthand for your ignorance, not a feature of the physics. With enough information, you could predict the outcome. In standard quantum mechanics, the probabilities seem to be irreducible. The theory does not provide a way to calculate which specific outcome will occur, only the distribution of outcomes over many measurements. This is interpretation dependent at the ontology level, meaning different interpretations of quantum mechanics disagree about what this implies for reality. But the prediction itself is clear: probabilities, not certainties. For decades, this was taken to mean that nature is fundamentally random at the quantum scale. The universe, it seemed, does not determine exactly what will happen, only what is likely to happen. I remember when I first encountered this idea, and it felt deeply strange. Every experience of cause and effect, every intuition about how things work, seemed to conflict with the claim that outcomes could be genuinely undetermined. Drop a ball and it falls. Push a cart and it moves. Causes produce effects. How could the fundamental level be different? The answer physicists gave was that quantum mechanics simply is different. Our intuitions are built from experiences at macroscopic scales, where quantum effects average out. At the fundamental level, randomness is real. This remains the mainstream position. What complicates it is a question that goes back to Einstein and was sharpened by the physicist John Bell. Is the theory complete? Could there be hidden variables, additional information beyond the wave function that would restore determinism if we knew them? Hidden variable approaches add additional variables, often written with the Greek letter lambda, intended to restore a more detailed description of outcomes than the wave function alone provides. The idea is straightforward. Perhaps quantum mechanics is like classical coin flipping. The probabilities reflect our ignorance rather than genuine indeterminism. Perhaps there are hidden causes, variables we do not measure and cannot currently access, that determine which specific outcome occurs. The wave function would then be an incomplete description, a statistical summary rather than a complete picture of reality. If hidden variables exist, then randomness is not fundamental. It is apparent randomness arising from hidden causes, just as the apparent randomness of a coin flip arises from hidden causes we choose not to measure. Some hidden variable theories can be deterministic, while still reproducing all the statistical predictions of quantum mechanics. They can match every probability, every correlation, every experimental result that standard quantum theory predicts. The outcomes would be determined by the hidden variables, and quantum randomness would be revealed as a kind of illusion, the appearance of chance masking an underlying causation. This sounds like exactly what Einstein hoped for, a restoration of determinism beneath the probabilistic surface. There is a problem, though, and it comes from John Bell. Bell-style arguments show that local hidden variable models cannot reproduce all quantum correlations if certain assumptions hold. The key word is local. Locality means that causes propagate at or below the first speed of light, that events in one region cannot instantaneously influence distant events. The speed of light is 299,792,458 meters per second, approximately 186,282 miles per second. Nothing travels faster than light, and no causal influence can propagate faster than light. This is a cornerstone of relativity, one of the most thoroughly tested principles in physics. Bell showed that if you combine locality with another assumption, measurement independence, then hidden variable theories make predictions that differ from quantum mechanics. Experiments can distinguish between the two. The experiments have been done many times with increasing precision. The results match quantum mechanics and violate the predictions of local hidden variable theories. The 2022 Nobel Prize in Physics was awarded for experiments on entanglement and Bell inequalities, work that tested and confirmed quantum predictions with unprecedented rigor. This seems to close the case. If local hidden variables cannot reproduce quantum mechanics, and experiments confirm quantum mechanics, then either randomness is fundamental or something else must give. Let me explain what Bell tests actually measure, because the logic is subtle and important. Imagine two particles created together in a special state called an entangled state. These particles are sent in opposite directions to distant detectors. At each detector, an experimenter chooses a measurement setting, essentially an orientation along which to measure some property of the particle. The particles are separated far enough, and the measurements are made quickly enough that no signal travelling at or below the speed of light could connect them. The events are space-like separated, meaning they are outside each other's light cones. Whatever happens at one detector cannot causally influence what happens at the other detector, assuming locality holds. Quantum mechanics predicts correlations between the measurement results that depend on the detector settings. If both detectors are oriented the same way, the results are perfectly correlated. If the settings differ, the correlations follow a specific pattern. Bell proved that any local hidden variable theory makes different predictions about these correlations. The correlations predicted by local hidden variables are bounded by an inequality, now called a Bell inequality. Quantum mechanics predicts correlations that violate this inequality. When experiments measure the correlations, they match quantum mechanics and violate the Bell inequality. The violations are not small or marginal, but clear and consistent across many experiments. This appears to rule out local hidden variables. Either the hidden variables do not exist, or they are not local, or some other assumption of the Bell argument fails. Most physicists interpret this as evidence that quantum randomness is fundamental. There are no hidden causes beneath the probabilities. The indeterminism is real. There is another possibility, though, one that is less discussed and more controversial. The Bell argument relies on an assumption called measurement independence. And if that assumption fails, the conclusion does not follow. Let me go deeper into how Bell tests actually work, because the details matter for understanding what they do and do not prove. The basic setup involves creating pairs of entangled particles. These particles are in a correlated quantum state, meaning the outcome of measuring one particle is correlated with the outcome of measuring the other, even when they are far apart. In a typical experiment, the entangled particles are photons. Two photons are created together in a state where their polarizations are correlated. If you measure the polarization of one photon along a particular axis and get a result, the other photon will give a correlated result when measured. The crucial point is that the correlations depend on the angle between the measurement axes at the two detectors. If the detectors are aligned, the correlations are perfect. If they are at different angles, the correlations follow a specific pattern predicted by quantum mechanics. Bell's insight was to show that any local hidden variable theory makes a different prediction about these correlations than quantum mechanics does. Specifically, local hidden variable theories predict that the correlations are bounded by certain inequalities. Quantum mechanics predicts that these inequalities can be violated. The experiments measure the correlations for different combinations of detector angles. They compare the measured correlations to the bounds predicted by local hidden variable theories. If the correlations exceed the bounds, the local hidden variable prediction is falsified. The results are consistent across many experiments over decades. The correlations match quantum mechanics. They exceed the bounds predicted by local hidden variables. The Bell inequality is violated. What does this prove? It proves that local hidden variable theories cannot reproduce the observed correlations if measurement independence holds. This is the key conditional. The derivation of the Bell inequality assumes that the measurement settings are statistically independent of the hidden variables. If they are not independent, the derivation does not apply, and the violation of the inequality does not rule out hidden variables. Let me explain why measurement independence is assumed and why denying it is controversial. When an experimenter chooses a measurement setting, the choice might be based on a coin flip, a random number generator, a human decision, or any number of factors. The assumption is that whatever determines the choice is unrelated to the hidden variables that the particles carry. This seems obvious at first. The choice is made by the experimenter, possibly influenced by random processes. The particles were created elsewhere, possibly far away. How could the choice and the particle properties be correlated? The superdeterministic answer is that they are correlated through common causes in the past. In a deterministic universe, everything that happens is determined by prior conditions. The experimenter's choice and the particle's properties both trace back to earlier states of the universe. If those earlier states had correlations built in, those correlations could persist and connect seemingly unrelated events. This is not a claim about conspiracies or spooky influences. It is a claim about the structure of a deterministic universe. If the initial state had certain correlations, those correlations would manifest in seemingly independent events later. The controversy is about whether such correlations are plausible. Critics argue that the correlations would have to be extraordinarily fine-tuned. The initial state would have to know what measurements would be made billions of years later in order for the correlations to produce quantum-like results. Defenders argue that in a deterministic universe, talking about the initial state, knowing the future, is misleading. The future follows from the initial state by deterministic evolution. The correlations are not predictions or intentions, but consequences of how everything unfolds. This is the conceptual core of the debate. Does the observed violation of Bell inequalities prove fundamental randomness, or does it only constrain the form that hidden variables could take? So, the mainstream view is that it proves fundamental randomness, that local hidden variables are ruled out, and that the most straightforward interpretation is that quantum outcomes are genuinely undetermined. The minority view is that the proof depends on measurement independence, which is an assumption that could fail if the universe is thoroughly deterministic. The violation of Bell inequalities proves only that local hidden variables are ruled out under certain assumptions, not that they are ruled out in general. Both views can claim support from the same experimental evidence. The difference is in how the evidence is interpreted and which assumptions are taken as secure. Let me go deeper into what the Born rule actually says, because understanding this is essential to understanding the randomness debate. The Born rule is the prescription in quantum mechanics that tells you how to calculate probabilities from the wave function. If you have a quantum system described by a wave function, and you want to know the probability of finding the system in a particular state upon measurement, you take the square of the amplitude of the wave function for that state. This rule was proposed by Max Born in 1926, and it has been confirmed by countless experiments. Every time physicists make quantum predictions, they use the Born rule. Every time those predictions are tested, they match observations. The Born rule is one of the most thoroughly confirmed elements of quantum mechanics. What the Born rule gives you is probabilities, not certainties. If the amplitude for a particular outcome is 1/2, then the probability is 1/4, and the outcome will occur about 1/4 of the time over many trials. The theory does not tell you which specific trial will give which outcome. This probabilistic character is what makes quantum mechanics different from classical mechanics. In classical mechanics, if you know the initial conditions precisely, you can calculate what will happen. In quantum mechanics, even with complete knowledge of the wave function, you can only calculate what is likely to happen. The question is whether this probabilistic character is fundamental or whether it reflects our ignorance of some deeper level of description. Standard quantum mechanics says the probabilities are fundamental. The wave function is the complete description of a quantum system, and the probabilities it yields through the Born rule are irreducible. There is no additional information that would make outcomes predictable. Hidden variable interpretations say the probabilities reflect ignorance. There are additional variables beyond the wave function that determine which specific outcome occurs. If we knew those variables, we would know exactly what would happen. The Born rule would be an emergent statistical pattern, like the laws of thermodynamics that emerge from ignoring molecular details. The Bell tests constrain hidden variable interpretations. They show that if hidden variables exist and are local, they cannot reproduce quantum predictions unless measurement independence fails. This leaves three options: accept fundamental randomness, accept non-local hidden variables, or deny measurement independence. Let me explain what local means in this context, because it is often misunderstood. Locality is the principle that causal influences propagate at or below the speed of light. An event at one location cannot instantaneously affect an event at a distant location. This is a cornerstone of special relativity and is built into our best theories of particle physics. Local hidden variables would be variables that travel with particles and determine measurement outcomes based only on local information. The particle carries its hidden variable with it, and the measurement outcome depends only on that hidden variable and the local detector setting. Bell showed that such local hidden variables cannot reproduce all quantum correlations. The correlations predicted by quantum mechanics between distant measurements are stronger than any local hidden variable theory can produce if measurement independence holds. This is often described as proving that quantum mechanics is non-local, but this is misleading. What Bell showed is that local hidden variable theories are ruled out under certain assumptions. Whether quantum mechanics itself is non-local depends on interpretation. In standard quantum mechanics, entangled particles exhibit correlations that cannot be explained by local hidden variables. But these correlations do not allow faster-than-light signaling. The correlations are non-local in a statistical sense, but no information can be transmitted faster than light. This is called quantum non-locality, and its relationship to relativistic causality is subtle. In Bohmian mechanics, there are explicit non-local influences. The velocity of a particle depends on the positions of distant particles. This is non-locality in a stronger sense, though it still does not allow faster-than-light signaling. In superdeterminism, there is no non-locality. The correlations arise from initial conditions, not from influences across space. Local causation is preserved because measurement independence is denied. Understanding these distinctions is important for understanding what the randomness debate is really about. The question is not whether quantum correlations are strange, which they are, but how to interpret them as evidence for fundamental randomness, as evidence for non-local hidden variables, or as evidence that our measurement choices are not independent of what we measure. All these options are on the table. All are consistent with experimental evidence. The choice between them is currently a matter of interpretation, not empirical test. Measurement independence is the assumption that measurement settings are statistically independent of the hidden variables. In simpler terms, it assumes the experimenter's choice of detector orientation is not correlated with the properties of the particles being measured. This seems obviously true. The experimenter decides what setting to use. How could that choice be correlated with the hidden variables that the particles carry? The decision might be made by a random number generator, a coin flip, a human whim. How could it be connected to variables that were set when the particles were created, possibly far away and long ago? Superdeterminism denies measurement independence. It claims that the measurement settings are not statistically independent of the hidden variables. The experimenter's choice and the particle's properties are correlated, not because one causes the other, but because both trace back to common causes in the past. If measurement independence fails, Bell's argument does not go through. The derivation of the Bell inequality uses the independence of settings and hidden variables. If they are correlated, the inequality need not hold, and the violation of the inequality does not prove that local hidden variables are impossible. This is the logical loophole. Superdeterminism offers a way to maintain locality and determinism in the face of Bell test results. The apparent randomness would arise from hidden variables that are correlated with measurement choices, making the correlations appear non-local without actually being non-local. You might wonder how measurement settings could possibly be correlated with particle properties. The settings are chosen by experimenters, by random number generators, by processes that seem completely unrelated to quantum particles. The superdeterministic answer is that nothing is unrelated. In a deterministic universe, everything traces back to initial conditions. The experimenter's brain states, the random number generator's output, the particle's hidden variables, all of these are determined by prior causes, which are determined by earlier causes all the way back. If the universe is deterministic from its earliest moments, then correlations between seemingly unrelated events are not only possible, but inevitable. The experimenter's choice and the particle's properties both emerge from the same initial conditions, the same web of cause and effect stretching back to the beginning. This is why it is called superdeterminism. It is not just determinism at the quantum level, but determinism so thorough that it includes the measurement process itself. The choices experimenters think they are making freely are actually determined, and those determined choices are correlated with the determined properties of the particles. I should be clear about the status of this idea. Superdeterminism is widely treated as a logical loophole, acknowledged as a gap in the Bell argument, but also controversial. The concerns are about testability, fine-tuning, and how to justify the needed correlations without building them in by hand. Let me address each of these concerns. Testability is a major issue. If measurement settings are correlated with hidden variables in a way that mimics quantum randomness, how would we ever know? Any experiment we do uses measurement settings, and those settings would be correlated with the hidden variables by hypothesis. It seems like superdeterminism could explain any result, which makes it hard to test. Some physicists argue this makes superdeterminism unfalsifiable and not scientific as a result. Others argue that specific superdeterministic models might make testable predictions that differ from standard quantum mechanics in some regime. The debate is ongoing. Fine-tuning is another concern. For superdeterminism to work, the correlations between measurement settings and hidden variables must be precisely tuned to reproduce quantum predictions. How did these correlations arise? What mechanism established them? Without a dynamical explanation, it seems like the correlations are just assumed, built into the theory by hand to match observations. Critics argue this makes superdeterminism circular. It explains away the Bell test results by postulating correlations that are designed to explain away the Bell test results. Defenders argue that all physics involves assumptions about initial conditions, and superdeterminism simply makes a different assumption than standard physics. The justification problem is related. Why should initial conditions be set up to produce these specific correlations? In standard cosmology, initial conditions are thought to be simple, not finely correlated in ways that track what experiments will be done billions of years later. Superdeterminism requires correlations stretching across the entire history of the universe, connecting events separated by vast distances and times. This is the part that most physicists find implausible. It seems to require the initial state of the universe to know what measurements will be made later, not in any conscious sense, but in the sense that the correlations must be present from the beginning to produce quantum-like results. Despite these concerns, a minority of serious physicists argue that superdeterminism deserves reconsideration. Hossenfelder and Palmer explicitly argue for rethinking superdeterminism and discuss what would be needed for a serious, testable research program. Tufte discusses deterministic approaches, often in a cellular automaton framing, tied to superdeterministic ideas. The argument for taking superdeterminism seriously is that the alternatives are also strange. Standard quantum mechanics accepts fundamental randomness, which means accepting that the universe contains irreducible chance, events without causes. Non-local hidden variable theories, like Bohmian mechanics, accept faster-than-light influences, which conflicts with the spirit of relativity. Superdeterminism accepts thoroughgoing determinism, which conflicts with intuitions about free will and independent choices. All options are strange. The question is, which strangeness is acceptable? Let me explore the historical context more deeply, because the debate about quantum randomness has been ongoing since the founding of quantum mechanics. In the early decades of the 20th century, physics underwent a revolution. Classical mechanics, which had described the motion of objects for over 2 centuries, gave way to quantum mechanics at the smallest scales. The new theory was spectacularly successful at predicting experimental results, but deeply strange in its implications. The standard interpretation of quantum mechanics, developed primarily in Copenhagen by Niels Bohr and colleagues, accepted probabilities as fundamental. When you measure a quantum system, the theory gives you probabilities for different outcomes. Before measurement, the system is in a superposition of possibilities. After measurement, it is in a definite state. But which state it ends up in is not determined by anything prior. This was a radical departure from classical physics, where the future follows deterministically from the past. In classical mechanics, if you know the positions and momenta of all particles at one instant, you can calculate their positions and momenta at any future instant. The future is contained in the present, mathematically speaking. Quantum mechanics broke this pattern. Even with complete knowledge of the wave function, you cannot predict exactly what will happen when you measure the system. The best you can do is calculate probabilities. Einstein had profound doubts about this picture. He accepted that quantum mechanics made accurate predictions. What he questioned was whether the theory was complete, whether it told the whole story about physical reality. His doubts are often summarized in historical discussions. He believed that physics should provide a complete description of reality, and he did not believe that reality could be fundamentally probabilistic. There had to be something beneath the quantum probabilities, some deeper level of description that would restore determinism. It is historically accurate that Einstein had major objections to quantum indeterminism and completeness. His objections led to famous debates with Bohr that shaped the interpretation of quantum mechanics. I should be careful about what can be claimed here. Einstein's views were complex and evolved over time. He was not simply a stubborn classicist refusing to accept new physics. He understood quantum mechanics deeply and raised serious challenges that took decades to address. One of his most famous challenges was the EPR paper, published in 1935 with Podolsky and Rosen. The paper argued that if quantum mechanics were complete, it would imply instantaneous influences between distant particles, which seemed to conflict with relativity. This was meant as a reductio ad absurdum, showing that quantum mechanics must be incomplete. The response from Bohr and others was to accept the strange correlations as features of quantum reality, rather than signs of incompleteness. The debate remained unresolved during Einstein's lifetime. John Bell's work in the 1960s transformed the debate from philosophy to physics. Bell showed that the question of hidden variables could be tested experimentally. If hidden variables existed and were local, experiments would give different results than quantum mechanics predicted. The experiments came later, with increasingly refined versions over decades. They consistently confirmed quantum predictions and violated Bell inequalities. This was taken as evidence against local hidden variables and in favor of fundamental quantum randomness. Einstein died in 1955, before Bell's theorem and before the decisive experiments. We do not know exactly what he would have made of these developments. Some speculate he would have accepted the results as ruling out the particular version of hidden variables he had in mind. Others speculate he would have found alternatives, perhaps something like superdeterminism. What we can say is that Einstein's instinct about determinism remains a live option within physics. The question he asked, whether quantum mechanics is complete, has not been definitively answered. Superdeterminism keeps Einstein's question alive by proposing that the apparent randomness arises from hidden causes we cannot access. This is not to claim that Einstein endorsed superdeterminism specifically. Such a claim would require primary source citations that do not exist in the research available. What is accurate is that Einstein's doubts about quantum randomness were part of a long tradition of seeking deterministic explanations for apparently random phenomena. Let me discuss the physicists who advocate for superdeterminism in more detail, because their arguments deserve a fair hearing. Sabine Hossenfelder and Tim Palmer have explicitly argued for rethinking superdeterminism. Their work examines what would be needed for a serious, testable research program in this area. Their argument begins with the observation that rejecting superdeterminism is usually based on intuitions about free will and experimental independence, not on experimental evidence. These intuitions are strong, but intuitions have been wrong before in physics. Quantum mechanics itself violates many classical intuitions. They argue that superdeterminism should be evaluated as a scientific hypothesis, not dismissed based on philosophical preferences. If specific superdeterministic models can be developed, they should be tested. The question is whether the universe is deterministic, and this is an empirical question in principle, even if current experiments do not directly address it. Their work also addresses the fine-tuning objection. Critics argue that superdeterminism requires implausible correlations in initial conditions. Hossenfelder and Palmer respond that all physics involves assumptions about initial conditions. The question is not whether initial conditions are assumed, but whether the assumptions are justified. They point out that we do not know why the initial conditions of the universe were what they were. Cosmology describes the evolution of the universe from early times, but does not explain why the early universe had the properties it did. Superdeterminism adds one more constraint on initial conditions: correlations that produce quantum-like statistics. Whether this is more or less plausible than other constraints on initial conditions is a matter of judgment. There is no objective criterion that rules it out. Gerard 't Hooft, a Nobel laureate in physics, has also explored deterministic approaches to quantum mechanics. His work often uses a cellular automaton framing, where the fundamental dynamics are deterministic and discrete. The continuous, probabilistic appearance of quantum mechanics would emerge from coarse graining over the underlying discrete dynamics. 't Hooft's approach is tied to superdeterministic ideas because it seeks to restore determinism beneath quantum mechanics. The details are technical, but the motivation is similar: the belief that the apparent randomness of quantum mechanics is not fundamental, but arises from a deterministic substrate. These are serious physicists with serious arguments. They are not cranks or outsiders. They are trained in physics, have made important contributions to the field, and believe that the randomness question deserves more attention than it receives. Their minority position does not mean they are right. It means their arguments should be considered rather than dismissed. The question of whether randomness is fundamental is too important to settle by appeals to authority or consensus. What would it take for superdeterminism to become mainstream? At minimum, specific superdeterministic models would need to be developed that make testable predictions differing from standard quantum mechanics. Those predictions would need to be confirmed by experiment. The models would need to explain not just Bell test results, but the full range of quantum phenomena. This is a high bar. No superdeterministic model currently meets it. The challenge for advocates is to move from general arguments for plausibility to specific theories with predictive power. Until such theories exist, superdeterminism will remain a minority position. The mainstream will continue to accept fundamental randomness. The debate will continue in philosophy of physics, in foundational conferences, and in the margins of the field. What I find valuable in the superdeterministic challenge is the reminder that fundamental questions remain open. Physics has made extraordinary progress, but it has not answered all questions. The nature of quantum randomness is one of those open questions. The answers we accept today may not be the answers we accept tomorrow. This is not relativism. It is recognition that science is an ongoing process, not a finished product. Current understanding is the best we have, but it is subject to revision in light of new evidence and new ideas. The superdeterministic challenge is one of many reminders that we have more to learn. Let me tell you about the cosmic Bell tests, because they push the question of measurement independence to an extraordinary scale. The concern about measurement independence is that the settings and the hidden variables might be correlated through some local, recent common cause. Perhaps the experimenter's choice is influenced by local conditions that also affect the particle source. Perhaps the random number generator shares some unnoticed connection with the experimental apparatus. To address this, physicists designed experiments that use astronomical photons to choose measurement settings, pushing any possible common cause correlation far into the past. Some experiments use photons from high redshift quasars to determine which measurement setting to apply. A quasar is an extremely bright galactic nucleus powered by a supermassive black hole, visible from billions of light-years away. The photons arriving from quasars today were emitted billions of years ago. By using these ancient photons to choose settings, the experiments push any possible common cause back to the time when those photons were emitted. If measurement settings and hidden variables are correlated, the correlation would have to originate not from recent local causes, but from causes billions of years in the past. A prominent quasar-based cosmic Bell test reports a constraint corresponding to photons emitted roughly 7.8 billion years ago. Let me put that in perspective. 7.8 billion years is more than half the current age of the universe. The photons used to choose measurement settings in this experiment were emitted before Earth existed, before our Sun formed, before most of the stars you can see at night were born. In terms of distance, 7.8 billion light-years corresponds to approximately 7.38 times 10 to the 22nd power kilometers, or about 4.59 times 10 to the 22nd power miles. These are distances so vast they exceed any intuitive grasp. The cosmic Bell test results still match quantum mechanics. The correlations still violate Bell inequalities. If superdeterminism is correct, the correlations between measurement choices and hidden variables would have to have been established at least 7.8 billion years ago, stretching back to an era when the universe was less than half its current age. This is the part that still amazes me, even after years of thinking about it. Experiments performed on tabletops in laboratories are connected through the logic of Bell tests and the use of ancient photons to questions about the initial conditions of the universe. The cosmic Bell tests do not prove superdeterminism false. They constrain it. If superdeterminism is true, the correlations must be primordial, built into the universe from its earliest moments. No recent common cause could explain them. Some physicists see this as making superdeterminism even more implausible. The required correlations become increasingly fine-tuned as the look-back time increases. Others see it as showing that the question of determinism versus randomness cannot be separated from cosmology, from questions about how the universe began. Let me step back and consider what is really at stake in this debate. On one side, we have the mainstream position, quantum randomness is fundamental. The probabilities in quantum mechanics are irreducible. Events at the quantum level are genuinely undetermined, not caused by hidden variables. The universe contains true randomness. On the other side, we have the superdeterministic hypothesis. Quantum randomness is apparent, not real. The probabilities arise from hidden variables that are correlated with measurement choices. Events at the quantum level are determined, but the determining factors are inaccessible to us. The universe is thoroughly causal, with no true randomness anywhere. The experimental evidence is consistent with both positions. Bell tests confirm quantum predictions, but they do not rule out superdeterminism, because superdeterminism denies one of the assumptions needed to derive the Bell inequality. The choice between these positions is currently not empirical, but philosophical. It depends on what you find more plausible: fundamental randomness or hidden correlations stretching back to the origin of everything. Think about that for a moment before we continue. If randomness is fundamental, then there are events that simply happen without being caused by anything. The universe is not fully governed by cause and effect. Some outcomes are genuinely open until they occur. If superdeterminism is correct, then everything is caused, everything is determined, and what looks like randomness is just the appearance of indeterminism arising from our limited perspective. Cause and effect is real everywhere, at every scale, from quarks to galaxies. Neither option is comfortable. Fundamental randomness challenges our intuitions about causation. Superdeterminism challenges our intuitions about freedom and independence. Physics does not tell us which to accept. It tells us the constraints each option must satisfy. Let me put the scales involved in these experiments into perspective, because the numbers connect quantum laboratory experiments to cosmic timescales. The speed of light is 299,792,458 meters per second. This is exact in the modern SI system, not a measured value with uncertainty. It corresponds to approximately 186,282 miles per second, or roughly 670 million miles per hour. Nothing travels faster than light. No causal influence can propagate faster than light. If two events are separated so that no signal traveling at or below the speed of light can connect them in time, they are called space-like separated. Local causal influence cannot explain correlations between space-like separated events. Bell tests exploit this constraint. The measurements are made quickly enough and the detectors are far enough apart that no light-speed signal could travel from one measurement to the other before both are complete. If local hidden variables determine the outcomes, they must do so without any communication between the detectors at the time of measurement. The correlations observed in these experiments violate Bell inequalities. If local causation applies and measurement independence holds, these correlations should not exist. The fact that they do exist and match quantum predictions is what makes the debate about hidden variables and randomness so compelling. Cosmic Bell tests push this further. By using photons from quasars to determine measurement settings, they extend the constraint on measurement independence back into cosmic history. A quasar is an extremely luminous galactic nucleus, powered by matter falling into a supermassive black hole at the center of a distant galaxy. Quasars are visible from billions of light-years away because they emit enormous amounts of radiation. The photons arriving from quasars today were emitted billions of years ago. By using these photons to trigger measurement settings, experiments push any common cause between settings and hidden variables back to the time of emission. The prominent cosmic Bell test I mentioned reports photons emitted roughly 7.8 billion years ago. This is more than half the age of the universe. The light from these quasars has been traveling through space for longer than the solar system has existed. To visualize this distance, 7.8 billion light-years corresponds to approximately 7.38 times 10 to the 22nd power kilometers. That is 73,800 billion kilometers. In miles, it is approximately 4.59 times 10 to the 22nd power miles. These numbers exceed any everyday intuition. They are larger than the number of grains of sand on Earth. They represent distances across which entire galaxies appear as dim specks. The cosmic Bell test results still match quantum mechanics. The correlations still violate Bell inequalities. If superdeterminism explains the results, the correlations between measurement choices and hidden variables would have to trace back at least 7.8 billion years. This is the scale at which questions about determinism and randomness intersect with cosmology. The question of whether measurement independence holds becomes a question about the initial conditions of the universe. The question of whether randomness is fundamental becomes entangled with questions about cosmic origins. At the other end of the scale, consider the smallest time intervals discussed in physics. The Planck time is approximately 5.39 times 10 to the negative 44th power seconds. This is the time it takes light to travel one Planck length. And it is often mentioned as the scale at which quantum effects and gravitational effects both become important. For perspective, 1 second contains about 1.86 times 10 to the 43rd power Planck times. That is far more Planck times in a single second than there are seconds since the universe began. These scales are relevant because questions about determinism and randomness may connect to physics at the Planck scale. Our current theories of quantum mechanics and gravity do not work well together at these scales. The resolution of foundational questions may require new physics that operates at scales far below anything we can directly probe. The contrast in scales is striking. Cosmic Bell tests use photons from quasars billions of light-years away. The fundamental physics may involve times and distances at the Planck scale, 43 orders of magnitude smaller than a second. The question of randomness spans this entire range, from the cosmic to the Planck scale. Let me discuss the major interpretations of quantum mechanics, because the debate about randomness is closely tied to questions about what quantum mechanics means. The Copenhagen interpretation, which remains the most commonly taught view, accepts quantum probabilities as fundamental. The wave function describes what we can know about a system, and the probabilities it yields are irreducible. There is no deeper level of description that would make outcomes deterministic. Measurement causes the wave function to collapse to a definite state, and which state it collapses to is genuinely random. Many worlds interpretation, developed by Hugh Everett, takes a radically different approach. There is no collapse and no randomness. Instead, when a measurement is made, the universe splits into branches, one for each possible outcome. All outcomes occur, just in different branches. From within any branch, outcomes appear random because we cannot access other branches. The fundamental physics is deterministic. Bohmian mechanics, also called pilot wave theory, adds hidden variables to quantum mechanics. Particles have definite positions at all times, guided by the wave function through a deterministic equation. Quantum probabilities arise from our ignorance of the exact initial positions. The theory reproduces all quantum predictions, but does so deterministically. The price is non-locality. The guiding equation involves instantaneous influences across space. Superdeterminism, as we have discussed, denies measurement independence rather than locality. It allows for local deterministic hidden variables by accepting that measurement choices are correlated with the hidden variables. The correlations arise from initial conditions rather than instantaneous influences. These interpretations make the same predictions for quantum experiments in most cases. They differ in what they say is really happening, what exists, and how causation works at the fundamental level. This is a remarkable situation. Multiple incompatible pictures of reality all reproduce the same experimental predictions. Physics, which usually distinguishes between competing theories by testing them, cannot currently distinguish between these interpretations. Some physicists argue that interpretations are mere philosophy, that what matters is the predictions, and that arguing about what the predictions mean is pointless metaphysics. Others argue that interpretation matters, that understanding what is really happening is part of understanding physics, and that the choice of interpretation has implications for how physics develops. The debate about randomness cuts across this divide. If you accept Copenhagen, randomness is fundamental, and there is nothing more to say. If you accept many worlds, randomness is apparent because all outcomes occur. If you accept Bohmian mechanics, randomness arises from ignorance of initial positions. If you accept superdeterminism, randomness arises from ignorance of hidden variables correlated with measurement choices. Each interpretation offers a different answer to the question of whether randomness is real. What I find striking is that these different answers have coexisted for nearly a century without experimental resolution. The question of randomness is not just technically difficult, but touches on deep issues about what science can establish and what remains a matter of interpretation. The cosmic Bell tests I mentioned earlier are attempts to narrow the options. By pushing measurement independence constraints back billions of years, they make some forms of superdeterminism less plausible by requiring the correlations to be primordial. They do not rule out superdeterminism entirely, but they raise the stakes for superdeterministic explanations. Let me discuss Bohmian mechanics in more detail, because it offers a different path to determinism than superdeterminism. In Bohmian mechanics, particles always have definite positions. The wave function does not just encode probabilities, but plays a physical role. It guides the particles through space. The guiding equation tells each particle how to move based on the wave function and the positions of all other particles. This guidance is non-local. The velocity of a particle at one location depends instantaneously on the positions of particles everywhere. This conflicts with the spirit of relativity, which says nothing can influence events faster than light. Bohmians argue that this non-locality is hidden. It does not allow faster-than-light signaling because we cannot control the initial positions precisely enough to send signals. The non-locality affects the statistics of outcomes, but does not let us transmit information. The quantum probabilities in Bohmian mechanics arise from the distribution of initial positions. If the initial positions are distributed according to a specific rule, called quantum equilibrium, then the statistics of outcomes match standard quantum predictions exactly. The randomness is apparent, arising from our ignorance of where particles started. Superdeterminism differs from Bohmian mechanics in a crucial way. Bohmian mechanics accepts non-locality and uses it to maintain determinism. Superdeterminism denies non-locality and instead denies measurement independence to maintain determinism. Both approaches restore determinism. They do so by accepting different modifications to standard assumptions. Bohmian mechanics modifies locality. Superdeterminism modifies measurement independence. This illustrates a general point about Bell's theorem. The theorem shows that local hidden variable theories cannot reproduce quantum predictions if measurement independence holds. To escape this conclusion, you must give up something: locality, as in Bohmian mechanics, or measurement independence, as in superdeterminism, or realism about hidden variables, as in Copenhagen and many worlds. There is no free lunch. Each option has a cost. The question is, which cost is acceptable? Let me explain entanglement in more detail, because it is the phenomenon that makes Bell tests possible. Entanglement is a quantum correlation between particles that is stronger than any classical correlation could be. When two particles are entangled, the properties of one particle are correlated with the properties of the other, even when they are far apart. Here is a simple example. Two photons can be created in an entangled state, where their polarizations are correlated. If you measure the polarization of one photon along a particular axis and find it horizontally polarized, the other photon will be found vertically polarized when measured along the same axis, or vice versa. The outcomes are perfectly anti-correlated. This might not seem surprising. Perhaps the photons were created with opposite polarizations from the start, and the measurements simply reveal what was already there. This is the hidden variable picture. The particles carry their properties with them, and measurement reveals pre-existing values. The strange thing is that the correlations hold for any measurement axis you choose. If you measure both photons along any axis, the outcomes are anti-correlated. This is true even if you choose the axes randomly. even if you choose them at the last moment, even if the photons are far apart when the measurements are made. Bell's insight was that local hidden variable theories cannot reproduce these correlations for all possible measurement axes. The correlations predicted by quantum mechanics, when summed over different axis choices, exceed a bound that any local hidden variable theory must satisfy. When experiments test these correlations, they find values that exceed the Bell bound. The correlations are stronger than local hidden variables could produce. This is the experimental evidence that is interpreted as ruling out local hidden variables. I want to be clear about what is and is not proven by these experiments. What is proven is that the quantum predictions are correct. The experiments confirm that entangled particles exhibit correlations that match quantum mechanics and violate Bell inequalities. What is not proven is that there are no hidden variables. The derivation of Bell inequalities assumes measurement independence. If measurement independence fails, hidden variables can produce any correlations whatsoever, including quantum correlations. The experiments prove that local hidden variable theories are ruled out if measurement independence holds. This is a conditional claim. The condition is an assumption, not an established fact. Superdeterminism denies the assumption. It says measurement settings are not independent of hidden variables. The choices we make about what to measure are correlated with the properties of the particles we measure. This correlation allows local hidden variables to produce quantum correlations. Let me explain why measurement independence seemed obviously true to most physicists. The measurement settings are chosen by experimenters, by random number generators, by various processes that seem completely unrelated to the quantum particles being measured. How could the choice of detector orientation be correlated with the hidden variables that photons carry? The superdeterministic answer is that in a deterministic universe, nothing is unrelated. The experimenter's choice traces back through a chain of causes to earlier states of the universe. The photon's hidden variables also trace back to earlier states. If those earlier states had correlations built in, the correlation between choice and hidden variable would persist. This is not a claim about conspiracy or intelligent design. It is a claim about the structure of determinism. In a deterministic universe, correlations established in initial conditions persist through time. If the initial conditions had the right correlations, quantum-like statistics would emerge from deterministic local physics. The question is whether such correlations are plausible. Most physicists find them implausible because they would have to be precisely tuned to produce quantum statistics. The initial state would have to contain correlations that track what measurements will be made throughout cosmic history. Superdeterminists argue that this objection begs the question. If we are asking whether the universe is deterministic, we should not assume that initial conditions are uncorrelated. The correlations might be there, and the only way to find out is to test specific models rather than dismiss them based on intuitions. This is where the debate currently stands. The intuitions of most physicists favor rejecting superdeterminism. A minority argues that intuitions should not override the logical possibility and that specific superdeterministic models should be developed and tested. Let me return to Laplace's Demon, because the thought experiment illuminates what is really being claimed. Laplace described a hypothetical intelligence that knows all forces acting in nature and the precise position of every particle at one instant. For this intelligence, Laplace wrote, nothing would be uncertain, and the future, like the past, would be present to its eyes. This is determinism in its purest form. Given complete knowledge of the present state and the laws of physics, the entire history, past and future, follows with mathematical necessity. Randomness exists only for beings with incomplete knowledge. True randomness does not exist. Quantum mechanics seem to refute this picture. The theory says that even with complete knowledge of the wave function, you cannot predict exactly which measurement outcome will occur. The theory gives probabilities, not certainties. There is no hidden knowledge that would make the outcomes predictable. Superdeterminism reclaims Laplace's vision. It says the appearance of quantum randomness arises because we lack access to the hidden variables. If we knew the hidden variables, we would know exactly what would happen. The demon with complete knowledge would see no randomness at all. The difference from Laplace's original picture is that the hidden variables include correlations with measurement choices. The demon would have to know not just the state of the particles, but the state of everything that determines what measurements will be made, all the way back to initial conditions. This is a more radical determinism than Laplace imagined. Not because it adds new claims, but because it extends the same claim to the measurement process itself. The experimenter's choices are part of the deterministic chain, not outside it. Pause for a moment and really try to picture what this means. If superdeterminism is correct, then when a physicist decides to set a detector to a particular orientation, that decision was determined by prior causes. Those prior causes were determined by earlier causes. The chain extends back through the physicist's education, childhood, ancestors, the formation of Earth, the collapse of molecular clouds, the nucleosynthesis in ancient stars, the conditions after the earliest moments of cosmic history. The measurement choice and the particle's hidden variables are both links in the same causal chain, the same web of determination stretching back to the beginning. Their correlation is not a coincidence or a conspiracy, but a consequence of everything being connected through cause and effect. This is why superdeterminism is sometimes called the free will loophole. If measurement choices are determined rather than free, the Bell argument does not apply. The loophole is the assumption of measurement independence, which is related to the assumption that experimenters can make genuinely free choices about what to measure. I want to be careful here about what is and is not being claimed. Superdeterminism does not require belief in or denial of free will in the philosophical sense. The question is narrower. Are measurement choices statistically independent of hidden variables? This is an empirical question, not a metaphysical one, even if the answer has metaphysical implications. It is possible to accept superdeterminism while being agnostic about free will. You could believe that measurement choices are determined without believing that human decisions are unfree in any sense that matters for ethics or personal responsibility. The levels of description might not connect in the way casual discussions assume. What superdeterminism does require is accepting that what looks like random experimental outcomes are actually determined by causes stretching back to the initial conditions of everything. The randomness is apparent, not real. Cause and effect operates everywhere. Let me discuss what proponents of superdeterminism actually propose. Hossenfelder and Palmer have explicitly argued for rethinking superdeterminism and discuss what would be needed for a serious, testable research program. Their argument is that superdeterminism should not be dismissed based on intuitions about free will or independence, but should be evaluated as a scientific hypothesis. What would a testable superdeterministic theory look like? It would need to specify the hidden variables, explain their dynamics, and make predictions that differ from standard quantum mechanics in some testable regime. The predictions would need to be precise enough that experiments could confirm or refute them. At present, no fully developed superdeterministic theory exists that meets these criteria. There are ideas, frameworks, and research programs, but nothing that qualifies as a complete theory with testable predictions that differ from quantum mechanics. 't Hooft has discussed deterministic approaches, often in what he calls a cellular automaton framing, where the fundamental dynamics are deterministic and discrete. These ideas are tied to superdeterministic approaches, though the relationship to specific experimental predictions remains under development. The honest assessment is that superdeterminism remains a hypothesis, not an established result. The claim that true randomness is an illusion is not a conclusion of physics, but a minority position held by some serious physicists who believe the question deserves more attention than it receives. Let me step back and think about what causation means, because the debate between randomness and determinism is ultimately a debate about whether cause and effect is universal. In everyday experience, causation is central to how we understand the world. Push a ball and it rolls. Heat water and it boils. Turn a key and the engine starts. Causes produce effects. Effects follow from causes. The world makes sense because this pattern holds. Science extended this causal picture to phenomena beyond everyday experience. The motion of planets follows from gravitational forces. The behavior of gases follows from molecular collisions. The properties of materials follow from atomic structure. At every level, the same pattern held. Effects follow from causes according to laws. Quantum mechanics disrupted this pattern, or seemed to. Standard quantum theory gives probabilities rather than certainties. When a radioactive atom decays, the decay seems to have no cause. It simply happens, with a probability calculable from the theory, but no mechanism that determines when it will occur. This was deeply strange. How could something happen without a cause? Where did the outcome come from if it was not determined by prior conditions? Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation accepts that quantum events are genuinely indeterminate. The many worlds interpretation says all outcomes occur in different branches. Hidden variable interpretations say there are causes we do not access. Superdeterminism says the causes include correlations with measurement choices. What they share is an attempt to make sense of quantum predictions while preserving some notion of what is happening beneath the probabilities. The question of whether randomness is fundamental is really a question about whether the causal pattern extends all the way down. Is there a level at which causes stop and pure chance takes over? Or does cause and effect continue indefinitely, with apparent randomness arising from hidden complexity? I find both options worth taking seriously. If fundamental randomness exists, then the universe contains genuine novelty. Outcomes arise that were not determined by anything prior. The future is genuinely open, not just unknown. This might feel liberating, a universe with room for the truly new. If determinism extends all the way down, then the universe is a vast causal web, where everything connects to everything through chains of cause and effect. The future follows from the past with mathematical necessity. What happens was always going to happen, given the initial conditions and the laws. Neither picture is comfortable. Fundamental randomness means some things happen without reasons. Thoroughgoing determinism means the future is fixed, even if unknown. Both challenge deep intuitions about how reality works. The honest position is that we do not know which picture is correct. Experiments confirm quantum predictions, but experiments do not distinguish between genuine randomness and hidden determinism if the hidden variables are correlated with measurement choices in the right way. Let me talk about what this means for how we understand science itself. Science is often described as the search for causes. We observe phenomena and ask why they happen. We look for patterns, regularities, mechanisms that explain the observations. The ideal explanation traces effects back to causes and provides a complete account of why things are the way they are. Quantum mechanics disrupted this ideal. Standard quantum theory does not provide a complete account of why specific outcomes occur. It provides probabilities, distributions, statistical regularities, but not single-event explanations. Some physicists accepted this as a new kind of science, one that gives complete predictions without complete explanations. The probabilities are the explanation, and asking for more is a category mistake. Others, like Einstein, found this unsatisfying. They wanted a theory that explains not just the statistics, but each individual event. They wanted hidden variables, deeper causes, a restoration of the causal picture. Superdeterminism is one version of this desire for complete causal explanation. It says the quantum probabilities arise from hidden causes that include correlations with measurement choices. The causal picture is restored, at the cost of accepting that measurement choices are determined rather than free. This is the part that still amazes me, even after years of studying this. The question of whether randomness is fundamental is connected to questions about what explanation means, what science is, and what kind of universe we inhabit. It is not just a technical question about quantum mechanics, but a deep question about the nature of reality. Let me discuss the practical implications of the randomness question, because it is not purely theoretical. Quantum randomness is used in technology. Random number generators based on quantum processes are considered more secure than classical random number generators because quantum outcomes, according to standard theory, are genuinely unpredictable. If you use a classical random number generator, the numbers are actually produced by deterministic algorithms. With enough information about the algorithm and its initial state, someone could predict the sequence. This is called pseudo-randomness. The numbers look random, but are determined by hidden causes. Quantum random number generators exploit processes like radioactive decay or photon detection, where quantum mechanics says the outcomes are genuinely undetermined. If quantum randomness is fundamental, these generators produce true randomness that cannot be predicted even in principle. Cryptography relies on randomness for security. Keys must be unpredictable to attackers. If the keys are generated by deterministic processes, an attacker with enough information could potentially predict them. Quantum random number generators offer security based on the assumption that quantum randomness is fundamental. If superdeterminism is correct, this assumption might be wrong. The outcomes of quantum random number generators would be determined by hidden variables, and in principle, they could be predicted by something with access to those variables. The practical security might not be affected, since no one has access to the hidden variables, but the theoretical foundation would be different. This is not a current security concern. There is no evidence that anyone can predict quantum random number generator outputs. The practical security of these devices does not depend on resolving the interpretation of quantum mechanics. What it illustrates is that the question of randomness has implications beyond pure theory. The assumptions we make about fundamental physics feed into how we think about technology, security, and practical applications. Quantum computing is another area where foundational questions intersect with technology. Quantum computers exploit superposition and entanglement to process information in ways that classical computers cannot match. They are not just faster classical computers, but represent a fundamentally different approach to computation. The power of quantum computing partly comes from the way quantum mechanics handles possibilities. A quantum computer can explore many possible solutions simultaneously, in some sense, collapsing to a definite answer upon measurement. If superdeterminism is correct, the apparent indeterminism in quantum measurement is not real. This does not obviously undermine quantum computing, which works because of quantum mechanics regardless of interpretation. The computations work the same whether randomness is fundamental or apparent. What it might affect is our understanding of what quantum computers are doing. Are they exploring genuinely open possibilities? Are they exploiting fundamental indeterminism? Or are they running deterministic processes that happen to produce useful correlations? These are interpretive questions rather than practical ones. Quantum computers work regardless of which interpretation is correct. The technology does not care about philosophy. What I find interesting is how technology can be built on physics that we do not fully understand at the foundational level. Quantum mechanics is extraordinarily successful as a predictive tool, even though the interpretation remains contested. Engineers can build devices based on quantum predictions without needing to resolve debates about randomness and determinism. This suggests that foundational questions, while important for understanding reality, may be orthogonal to practical applications. The universe behaves according to quantum mechanics. We can exploit that behavior even if we disagree about what it means. Let me also discuss how the randomness question relates to everyday notions of probability. In everyday life, we use probability to express uncertainty about events we cannot predict. Weather forecasts give probabilities of rain. Polls give probabilities of election outcomes. Doctors give probabilities of treatment success. These probabilities reflect our incomplete knowledge, not fundamental indeterminism. Quantum probabilities seem different. According to standard theory, they are not expressions of ignorance, but features of reality. There is no additional information that would make the outcomes predictable. The probabilities are the best possible description. Superdeterminism challenges this distinction. If quantum probabilities arise from hidden variables, they are more like everyday probabilities, expressions of ignorance about causes we cannot access. The difference is that the hidden causes are in principle inaccessible, not just practically unknown. This connects to broader questions about what probability means. Is probability always about knowledge, or can it be about reality? Can events be objectively probable without being subjectively uncertain? These are questions for philosophy of probability, and they intersect with questions about quantum mechanics. I do not have definitive answers to these questions. What I can offer is the observation that the debate about quantum randomness touches on deep questions about the nature of probability, knowledge, and reality. These questions have been debated for centuries and remain unresolved. Let me discuss what is known, what is unknown, and what is being actively investigated. What is known is the empirical situation. Quantum mechanics makes probabilistic predictions. Those predictions are confirmed with extraordinary precision by experiments across a vast range of phenomena. Bell tests show that local hidden variable theories cannot reproduce quantum predictions if measurement independence holds. Cosmic Bell tests push the measurement independence question back billions of years. What is unknown is whether measurement independence actually holds. No experiment directly tests this assumption because any test would use measurement settings, and those settings would be correlated with hidden variables by the superdeterministic hypothesis. The loophole is logical, not empirical. What is being actively investigated falls into several categories. First, some researchers are developing specific superdeterministic models to see if they make testable predictions. The goal is to move beyond the general hypothesis to concrete theories that could be confirmed or refuted. This is ongoing work without definitive results yet. Second, some researchers are exploring the relationship between superdeterminism and other areas of physics, particularly quantum gravity and cosmology. The question of initial conditions ties superdeterminism to questions about how everything began and why early conditions had the properties they did. Third, the measurement independence assumption itself is being examined more carefully. How much independence is needed for Bell arguments to work? What kinds of correlations would be needed to reproduce quantum predictions? This quantitative work clarifies what superdeterminism would have to accomplish. The The honest assessment is that the question remains open. Neither the existence nor the non-existence of fundamental randomness is established. Mainstream physics accepts quantum randomness as fundamental, but this acceptance is based on theoretical preferences and interpretive choices, not on experimental proof that rules out alternatives. Let me put this in perspective. Physics has been remarkably successful at explaining the world through cause and effect. From Newton's mechanics to Maxwell's electromagnetism to Einstein's relativity, the pattern has been consistent. Phenomena follow from laws and initial conditions in a deterministic way. Quantum mechanics broke this pattern, or appeared to. For a century, physicists have debated whether the break is real or only apparent. The debate continues because the evidence underdetermines the answer. Experiments do not tell us whether randomness is fundamental or arises from hidden causes. This is not a failure of physics, but a reflection of the depth of the question. We are asking about the ultimate nature of reality, about whether cause and effect is universal or has exceptions. These are the hardest questions, and it is not surprising that they resist easy answers. What I find remarkable is that we can even ask these questions, that experiments with entangled photons in laboratories connect to questions about determinism and randomness, about Laplace's Demon and the initial conditions of everything. The Planck time, approximately 5.39 times 10 to the negative 44th power seconds, is often mentioned in discussions of fundamental physics. This is the timescale at which quantum effects and gravitational effects are both important, the scale at which our current theories break down. Questions about determinism and randomness may ultimately connect to questions about quantum gravity and the fundamental structure of space and time. We do not yet have a complete theory of quantum gravity. We do not know how to combine quantum mechanics with general relativity in a fully consistent way. The answer to whether randomness is fundamental may depend on physics we have not yet discovered. This is the honest situation. The question is open. Serious physicists hold different views. The evidence is consistent with multiple interpretations. Progress requires theoretical development and potentially new kinds of experiments. Let me address a common misconception before we continue. Some people assume that the randomness debate is settled, that quantum mechanics proved determinism wrong, that Bell tests closed the case. This is not accurate. What Bell tests show is that local hidden variable theories are ruled out if measurement independence holds. This is a conditional claim. The condition, measurement independence, is an assumption that superdeterminism denies. Denying measurement independence is controversial and has its own problems. It is not clear how to build a testable superdeterministic theory. The required correlations seem to need fine-tuning. The approach challenges intuitions about experimental independence. All these concerns are legitimate. They explain why superdeterminism is a minority position. They do not show that superdeterminism is wrong. The honest claim is that we do not know whether randomness is fundamental. We know that standard quantum mechanics is probabilistic in its predictions. We know that local hidden variables are ruled out under specific assumptions. We do not know whether those assumptions hold. This uncertainty is not a weakness of physics, but an acknowledgement of what we actually know. The alternative, claiming certainty where uncertainty exists, would be intellectually dishonest. Let me explore, in more detail, why different physicists reach different conclusions about the same experimental evidence. The experiments are clear. Bell inequalities are violated. Quantum predictions are confirmed. Entangled particles show correlations that exceed what local hidden variable theories can produce under standard assumptions. Where physicists disagree is in interpreting what these results mean. One group, probably the majority, interprets the results as evidence for fundamental randomness. They accept that quantum mechanics is probabilistic at its core, that the Born rule gives irreducible probabilities, and that there are no hidden variables to discover. The violation of Bell inequalities confirms that local determinism fails. The universe contains genuine chance. Another group interprets the results as evidence for non-locality. They believe hidden variables exist, but those variables are not local. Bohmian mechanics is the main example. Particles have definite positions at all times, guided by the wave function through a non-local equation. The violation of Bell inequalities shows that locality fails, not that determinism fails. A third group interprets the results as leaving open the question of measurement independence. They point out that the derivation of Bell inequalities assumes measurement settings are independent of hidden variables. If this assumption fails, the violation of Bell inequalities does not rule out local determinism. Superdeterminism falls into this category. Each group has reasons for their position. Those who accept fundamental randomness argue that quantum mechanics has been extraordinarily successful without hidden variables. Adding hidden variables complicates the theory without adding predictive power. The simplest interpretation of the evidence is that there are no hidden variables, and randomness is fundamental. Those who favor non-local hidden variables argue that fundamental randomness is philosophically problematic. Events without causes are hard to understand. Non-local hidden variables restore causation, even if they require accepting non-local influences. The price is worth paying for a causally complete picture. Those who favor superdeterminism argue that non-locality is also problematic, especially in light of relativity. Local determinism preserves the causal structure of space-time. The price of denying measurement independence is worth paying if it preserves locality. Notice that each group is making a judgment about which price is acceptable. Fundamental randomness costs causation. Non-local hidden variables cost locality in a strong sense. Superdeterminism costs measurement independence. No option is free. This is why the debate persists. The experimental evidence constrains the options but does not select among them. The choice depends on which theoretical virtues are prioritized: simplicity, causation, locality, or independence. I want to emphasize that these are not empirical virtues, but theoretical ones. Simplicity, causation, locality, and independence are features we value in theories. But the universe does not owe us theories with these features. Reality might be genuinely random, or non-local, or superdeterministic, regardless of our preferences. The honest position is to recognize that current evidence does not settle the question. Different physicists make different judgments based on different values. The debate continues because reasonable people can disagree about which theoretical virtues matter most. Let me discuss what would change if new evidence emerged. If specific superdeterministic models made predictions that differed from standard quantum mechanics, those predictions could be tested. If the tests confirmed the superdeterministic predictions, that would be evidence for superdeterminism. If the tests confirmed standard predictions, that would be evidence against that particular superdeterministic model. Currently, no superdeterministic model makes such predictions. The challenge for superdeterminism advocates is to develop models that are testable, not just logically possible. Similarly, if new phenomena were discovered that violated quantum predictions, that could point toward alternatives, including hidden variable theories. No such phenomena have been found, but physicists continue to look. The situation is dynamic. New experiments, new theoretical developments, and new ideas could shift the debate. What seems settled might be overturned, and what seems speculative might become mainstream. This is how science works. Current consensus is provisional, based on current evidence and current theoretical understanding. Future discoveries can change everything. The question of whether randomness is fundamental is part of this ongoing process. It was asked a century ago, it remains open today, and it may be answered by physics we have not yet imagined. Let me discuss the 2022 Nobel Prize in Physics, because it provides important context for understanding the current state of the randomness debate. The 2022 Nobel Prize in Physics was awarded for experiments on entanglement and Bell inequalities. The Nobel Committee recognized work that tested and confirmed quantum predictions with unprecedented rigor, closing loopholes in earlier experiments and establishing the violation of Bell inequalities as a robust experimental fact. This work is significant because it moved the Bell test from a thought experiment to a precision measurement. Early Bell tests had loopholes, potential ways that local, hidden variables could still explain the results. Later experiments systematically closed these loopholes, making the violation of Bell inequalities more definitive. What does this mean for the randomness debate? The Nobel Prize recognizes that local, hidden variable theories are ruled out under specific assumptions. The experiments confirm that the correlations between entangled particles exceed what local hidden variables could produce if measurement settings are independent of hidden variables. The prize does not settle the interpretation question. The Nobel Committee did not declare that randomness is fundamental or that superdeterminism is ruled out. What they recognized is experimental achievement, the confirmation of quantum predictions, and the violation of Bell inequalities with high precision. This is an important distinction. The experiments establish a fact, the violation of Bell inequalities. But the interpretation of that fact remains contested. The fact is consistent with fundamental randomness, with non-local hidden variables, and with superdeterminism. Which interpretation is correct is not determined by experiment alone. I want to be clear that this is not a criticism of the Nobel Committee or the prize-winning work. The experiments are remarkable achievements. They took abstract theoretical questions and turned them into precision measurements. They closed loopholes that had persisted for decades. They established the quantum predictions as experimental facts, not just theoretical claims. What the experiments did not do, and could not do with current methods, is directly test measurement independence. The loophole that superdeterminism exploits remains logically open. The experiments constrain it by pushing any measurement independence violation back in time, but they do not close it. This is why the debate continues after the Nobel Prize. The prize-winning experiments advanced the field enormously, but did not resolve the interpretation question. That question remains for future work, future theories, and possibly future experiments. Let me also discuss how the scientific community responds to minority positions like superdeterminism. In any field, there is a mainstream view and there are minority views. The mainstream view in quantum foundations is that quantum randomness is fundamental, that hidden variables are ruled out by Bell tests, and that alternatives like superdeterminism are implausible. Minority views face challenges. They struggle for attention, for funding, for publication in top journals. The burden of proof is on the minority to show that the mainstream is wrong or incomplete. This is not necessarily unfair. Mainstream views become mainstream because they are supported by evidence and theoretical arguments. Minority views should be scrutinized carefully before they are accepted. At the same time, scientific progress sometimes comes from minority views. The history of physics includes examples where the mainstream was wrong and outsiders were right. This does not happen often, but it happens. Superdeterminism is a minority view. It faces skepticism from most physicists. Advocates argue that the skepticism is not justified by evidence, but by theoretical preferences that could be wrong. The honest assessment is that we do not know who is right. The mainstream might be correct that superdeterminism is implausible. Minority might be correct that superdeterminism deserves more attention. The question cannot be settled by counting votes, but only by developing theories and testing them. This is the nature of scientific inquiry. Consensus is valuable because it represents accumulated evidence and argument. Dissent is valuable because it challenges assumptions and opens new possibilities. The tension between consensus and dissent drives progress. The randomness debate exemplifies this tension. Mainstream physics accepts fundamental randomness. A minority questions this acceptance. Both sides contribute to the ongoing conversation about what quantum mechanics means and whether it is complete. Let me connect the randomness debate to broader questions in physics, because it does not stand alone. The question of determinism versus randomness is related to the measurement problem in quantum mechanics. The measurement problem asks, what happens when a quantum system is measured? The wave function describes superpositions of possibilities, but measurements give definite outcomes. How does the transition happen? Standard quantum mechanics says the wave function collapses upon measurement. The superposition of possibilities becomes a single definite outcome. But the theory does not explain how or why collapse happens. It simply postulates that measurement produces definite outcomes, with probabilities given by the Born rule. If hidden variables exist, the measurement problem might be solved. The outcomes were always determined by the hidden variables. There is no mysterious collapse, just the revelation of pre-existing values. The appearance of indeterminism arises from our ignorance of the hidden variables. This is part of what makes hidden variable interpretations attractive. They promise to explain not just the statistics of quantum mechanics, but the mechanism by which definite outcomes arise. Superdeterminism goes further. It not only explains how outcomes are determined, but does so while preserving locality. The correlations between distant measurements arise from initial conditions, not from non-local influences. Relativistic causality is maintained. Of course, the price is accepting that measurement choices are not independent of hidden variables. This is the trade-off at the heart of the interpretation debate. The question of randomness is also related to the arrow of time. In physics, most fundamental laws are time-symmetric. They work the same whether time runs forward or backward. Yet our experience has a clear direction. The past is fixed, the future is open. If randomness is fundamental, this might explain the arrow of time. Random events create new information, new facts that did not exist before. The future is open because genuinely random events have not yet occurred. The past is fixed because random events have been realized. If determinism holds all the way down, the arrow of time needs a different explanation. The future is not really open, but only seems open because we cannot calculate it. The distinction between past and future becomes epistemic rather than metaphysical. Both options have their own puzzles. Fundamental randomness raises questions about where the randomness comes from and what determines the probabilities. Thoroughgoing determinism raises questions about why we experience time as directional and why we feel we have choices. These puzzles are not resolved. They remain open questions in physics and philosophy. The randomness debate is one thread in a larger tapestry of questions about time, causation, and the nature of reality. Let me also mention the relationship to quantum gravity. Quantum mechanics and general relativity are our two most successful physical theories. Quantum mechanics describes the behavior of matter at small scales. General relativity describes gravity and the structure of space-time. Both are extraordinarily well confirmed by experiment. The problem is that the two theories do not fit together. When you try to apply quantum mechanics to gravity, or to include gravity in quantum field theory, you encounter mathematical inconsistencies. A complete theory of quantum gravity unifying the two frameworks does not yet exist. Some physicists believe that the resolution of quantum foundations may require quantum gravity. The question of randomness may look different in a theory that unifies quantum mechanics and gravity. The measurement problem may be connected to the nature of time in gravitational physics. The initial conditions that determine superdeterministic correlations may be constrained by a more fundamental theory. This is speculative. We do not have a complete theory of quantum gravity. and we cannot know how it would affect interpretive debates. What we can say is that foundational questions about quantum mechanics may be connected to open questions about gravity and space-time. The Planck scale, roughly 5.39 times 10 to the negative 44th seconds in time, and 1.6 times 10 to the negative 35th meters in length, is where quantum effects and gravitational effects are both important. This is far beyond current experimental reach. The physics at this scale may hold answers to questions we are currently asking with incomplete information. The humility appropriate to this situation is significant. We are asking whether randomness is fundamental using theories that we know are incomplete. The answer may require physics we have not yet discovered. The honest position is that we do not know, and we may not know for a long time. Let me connect these abstract ideas to everyday experience, because the question of randomness versus determinism is not purely academic. Consider a simple decision, like choosing what to have for breakfast. In everyday experience, this feels like a free choice. You could have toast, you could have cereal, you could skip breakfast entirely. Nothing forces you to choose one option over another. If determinism is true all the way down, then your choice was determined by prior causes. Your brain state at the moment of decision followed from earlier brain states, which followed from still earlier states, all the way back through your life history and beyond. The feeling of freedom is real as an experience, but the outcome was fixed by causes stretching back to initial conditions. If fundamental randomness exists, then somewhere in the causal chain there are genuinely undetermined events. Perhaps quantum fluctuations in your neurons contribute randomness to the decision process. The outcome was not fully determined by prior conditions because some of those conditions involved genuine chance. Which picture is correct matters for questions about responsibility, prediction, and control. If outcomes are determined, then in principle they are predictable. Laplace's demon could have known what you would have for breakfast this morning before you were born. Not because breakfast choices are important, but because they are part of the same causal web as everything else. If outcomes involve genuine randomness, then they are not fully predictable, even in principle. No intelligence, however complete its knowledge, could have predicted exactly what would happen, because some of what happens is not determined by prior conditions. I want to be clear that neither option has obvious implications for questions about moral responsibility or practical prediction. Philosophers debate these questions extensively, and there is no consensus that determinism or indeterminism has cleaner implications for ethics. The practical situation is that we cannot predict complex outcomes regardless of whether the underlying physics is deterministic or random. Weather, economics, human behavior, all of these are unpredictable in practice because we cannot track all the relevant variables. Whether the underlying physics is deterministic does not change this practical limitation. What the question does affect is our understanding of what kind of universe we inhabit. Is the future fixed by the past, or is it genuinely open? Is novelty built into reality, or is it only an appearance arising from our limited perspective? These are questions about the nature of reality, not about practical consequences. They matter because understanding reality matters, even when that understanding does not change what we do. Let me discuss another aspect of the debate: the role of probability in physics. Standard quantum mechanics uses probabilities in a way that seems to differ from classical probability. In classical physics, probability usually reflects ignorance. When you assign a 50% probability to heads on a coin flip, you are expressing incomplete knowledge of the physical factors that determine the outcome. With more information, you could predict better. In standard quantum mechanics, probabilities seem to be irreducible. The wave function gives you all the information there is about a quantum system, and it still only yields probabilities from measurement outcomes. This is not ignorance. According to the standard interpretation, it is the nature of quantum reality. Superdeterminism offers a different view. The quantum probabilities do reflect ignorance, specifically ignorance of the hidden variables. If you knew the hidden variables, you would know exactly what would happen. The probabilistic predictions of quantum mechanics are like the probabilistic predictions of coin flipping, accurate in aggregate, but concealing deterministic processes underneath. This has implications for what quantum mechanics means. Is it a complete theory of reality, or an effective theory that arises from deeper deterministic dynamics? Is the wave function a complete description of a quantum system, or a statistical summary of hidden variables we cannot access? These questions have been debated since the foundations of quantum mechanics were laid in the 1920s and 1930s. Einstein believed quantum mechanics was incomplete. Bohr believed it was as complete as physics could be. The debate continues, with superdeterminism offering one version of the incompleteness view. What would it mean for physics if superdeterminism were correct? First, it would mean that quantum randomness is not fundamental. The apparent randomness of quantum events would arise from hidden causes, and the universe would be deterministic at the deepest level. Second, it would mean that measurement independence fails. Experimental choices and quantum properties are correlated through chains of cause and effect stretching back to initial conditions. Experiments are not independent of what they measure. Third, it would mean that understanding initial conditions becomes even more important. The correlations needed for superdeterminism are set in the initial conditions, so understanding those conditions becomes central to understanding quantum physics. Fourth, would potentially connect quantum foundations to cosmology in new ways. The question of why initial conditions have the correlations they do becomes a question about the origin of everything. These would be significant shifts in how physics is understood. They explain both why superdeterminism is taken seriously by some and why it is resisted by many. Let me reflect on what makes this question so compelling, because it touches on something fundamental about how we understand the world. Cause and effect is the basic structure of explanation. When we ask why something happened, we are asking for causes. When we predict what will happen, we are reasoning from causes to effects. This pattern is so pervasive that it feels like a necessary truth about reality. Quantum mechanics challenges this pattern. Standard theory says that some events happen without causes, or at least without complete causes. A radioactive atom decays not because of any prior condition, but simply because quantum mechanics assigns a probability to decay. The event happens, but nothing made it happen at that particular moment. This is deeply strange. Our entire framework for understanding the world is built on causes producing effects. Events without causes seem to be exceptions to the rules of intelligibility. Superdeterminism preserves cause and effect at the cost of other intuitions. If measurement choices are determined along with everything else, then cause and effect extends everywhere. There are no uncaused events. The pattern of explanation remains intact. The price is accepting that our choices, including our choices about what to measure in physics experiments, are determined rather than free in some sense. This challenges intuitions about independence and control. Both options require revising intuitions. Fundamental randomness revises the intuition that events have causes. Superdeterminism revises the intuition that our choices are independent of what we are investigating. Neither revision is comfortable. This discomfort is itself informative. It suggests we are near the limits of our intuitive understanding, where the concepts that work for everyday experience may not apply to fundamental physics. I remember when I first encountered this set of ideas, and it took time to appreciate how genuinely strange the situation is. On one side, events without causes. On the other side, correlations stretching back to the beginning of time. Neither option fits neatly into ordinary experience. What keeps physicists engaged with these questions is the sense that something important is at stake. The question of whether randomness is fundamental is not just a technical issue about quantum mechanics. It is a question about the kind of universe we inhabit, about whether the future is open or fixed, about whether causation is universal or has limits. These questions matter beyond physics. They connect to debates about free will, about the nature of time, about whether the universe is fundamentally comprehensible. They are among the deepest questions humans have asked, and the fact that quantum mechanics touches on them gives physics a philosophical significance beyond its practical applications. Let me also acknowledge the limits of what this video can accomplish. I have explained the question of quantum randomness, the role of Bell tests, the logic of superdeterminism, and why the question remains open. I have not proven anything. I cannot prove whether randomness is fundamental or apparent, and neither can anyone else with current evidence. What I can do is present the situation honestly. The mainstream view is that quantum randomness is fundamental, and this view is supported by the success of quantum mechanics and the results of Bell tests. The minority view is that randomness is apparent and arises from hidden variables correlated with measurement choices. This view remains logically possible and is defended by serious physicists. The honest conclusion is uncertainty. We do not know whether randomness is fundamental. The question is genuinely open, genuinely difficult, and may remain unresolved for a long time. This uncertainty is not a failure of physics, but an accurate assessment of where we stand. Physics has made enormous progress in understanding the physical world. It has also encountered questions that resist easy answers. The question of randomness is one of them. What I find valuable in this situation is the example of honest inquiry. Rather than claiming certainty where none exists, physics acknowledges its limits. Rather than dismissing hard questions as unanswerable, physicists continue to investigate them. This combination of humility and persistence is a model for how to approach difficult questions. The universe does not owe us easy answers. Some questions may be forever beyond our reach. Others may require conceptual breakthroughs we have not yet achieved. The question of randomness may fall into either category. We do not know. What we can do is continue to investigate, to test our assumptions, to develop new ideas, and to remain honest about what we know and what we do not know. This is the best we can do, and it is enough to sustain genuine inquiry across generations. Let me discuss what the future might hold for this question. The debate between determinism and fundamental randomness is unlikely to be resolved soon, but progress is possible. Here are some directions that could advance understanding. First, new experiments could test quantum mechanics in regimes where it has not been tested. If there are deviations from quantum predictions, they might point toward specific alternatives, including some superdeterministic models. No such deviations have been found, but the search continues. Second, theoretical development could produce specific superdeterministic theories with testable predictions. Moving beyond the general hypothesis to concrete models would change the debate from philosophical to empirical. This is the challenge that proponents like Hossenfelder and Palmer emphasize. Third, progress in quantum gravity might shed light on foundational questions. The unification of quantum mechanics and general relativity could reveal new physics that affects how we understand randomness and determinism. This is speculative, but possible. Fourth, the measurement independence assumption could be probed more directly. While no experiment can definitively test this assumption, creative experimental designs might provide evidence that constrains superdeterministic models or makes them more plausible. The honest expectation is that the question will remain open for a long time. Foundational questions in physics often resist resolution for decades or centuries. The interpretation of quantum mechanics has been debated since the 1920s without reaching consensus. The question of determinism versus randomness may take equally long to resolve, if it can be resolved at all. What I find valuable in this situation is the honesty about uncertainty. We do not know whether randomness is fundamental. We do not know whether Laplace's vision of a deterministic universe is correct. We know the constraints, we know the options, and we know that current evidence does not decide between them. This is the state of human knowledge on one of the deepest questions about reality. It is not a failure, but an accurate assessment of where we stand. Let me bring this exploration to a close by returning to where we started. Laplace imagined an intelligence that knows everything about the present and can deduce everything about the past and future. For this demon, nothing would be uncertain. Randomness would not exist. Quantum mechanics seemed to banish Laplace's demon. The probabilities in quantum theory are not mere expressions of ignorance, but fundamental. features of the predictions. Even perfect knowledge of the wave function yields only probabilities, not certainties. Superdeterminism offers Laplace's demon a way back. If measurement choices are correlated with hidden variables, then the probabilities reflect ignorance after all. The demon, with complete knowledge, including knowledge of the hidden variables, would see no randomness. Cause and effect would extend everywhere. The question is, which picture is correct? Fundamental randomness or hidden determinism? Physics alone cannot answer this question with current evidence. The answer depends on assumptions that experiments do not directly test. Bell tests rule out local hidden variables if measurement independence holds. Superdeterminism denies measurement independence. The logical gap remains open. What we can say is that cause and effect, as we experience it in everyday life, is real. Push something and it moves. Heat something and it warms. Actions have consequences. This causal picture works extraordinarily well at the scales we inhabit. Whether this causal picture extends to the quantum level is less clear. Standard quantum mechanics says it does not, that genuine randomness enters at the quantum scale. Superdeterminism says it does, that the appearance of randomness hides deterministic causes we cannot access. Both options are intellectually coherent. Both face challenges. The choice between them is currently a matter of judgment and philosophical preference, not experimental verdict. This is what I find remarkable about this topic. We are at the edge of what we know. The question of whether randomness is fundamental is genuinely open, genuinely uncertain, genuinely deep. It connects quantum experiments to questions about the nature of causation, the meaning of probability, and the structure of reality. I want to leave you with an invitation rather than a conclusion. Think about what it would mean for randomness to be fundamental. Think about what it would mean for cause and effect to extend everywhere without exception. Consider which picture you find more plausible, more satisfying, more consistent with your understanding of the world. There is no right answer that I can give you. There is only the honest acknowledgement that we do not know, together with the remarkable fact that we can ask the question at all. Thank you for taking this journey with me through hidden variables and Bell tests, through cosmic experiments and superdeterminism, through questions that have been debated for a century and remain unresolved. These ideas deserve careful attention, and I appreciate you giving them that. If you found value in this exploration, consider subscribing to the channel. It helps these deep dives reach more curious minds. Sleep well tonight, and perhaps think about the question as you fall asleep. Are the events in your brain genuinely random or determined by causes stretching back to the beginning? We do not know. The question remains open, and that itself is remarkable. Good night.